So basically, I decided to do this experiment for real. Okay, now what I have here, it's about a 7.2 millihenry core. I guess around a kilohertz is what my tester said. So somewhere in that neck of the woods, but it is a laminate core, so it's going to be really lossy. Particularly at 5 kilohertz frequency, this expects. But that's a 100 nanofarad, 100 volt capacitor, and I've got it in series with a 10 ohm resistor, and I got my voltage on my power supply set to 2 volts, and it's current limited to about 45 milliamps where I got it now. I'm just trying to play things safe. Um, Now, when I charge this thing up, it gets down to, 0.46 or so volts across that 10 ohm resistor. So, like you'd expect, 46 millivolts, but, 45 milliamps. Um, so, or maybe it was, well, you do the math, okay? I'll show you in a minute. But this is the result, basically. So, I've got it set, my scope, the probes are 1x mode, alright? So, and I've got it set to 5 volts per division on the yellow trace. So that's about, a peak of 7-ish volts. And again, since this is such a lossy core, it'll damp out really quick, and that's what you're seeing. If it's about 50 microseconds per division. If you do the math on that, it does work out to be around 5 kilohertz. So that is an actual response. And anyway, if you took this peak, because even this peak is going to be damped, so it should actually get to a lower voltage. And at this rate, FileStat predicts it to be about, it should be about 22 volts peak to peak or something, with ideal components and all that crap, in a similar arrangement. But, this would be doing like 14 volts, but probably higher again if this weren't such a lossy core, I would imagine. So, but let's go ahead and, run a test here on it. So, let me get the. See, I couldn't do these experiments last year because I didn't have decent equipment, as decent as I have now, anyway. Um, Last year, let me get these probes out of the way here. All right, so here's my connector here, and I'm going to go ahead and short circuit it, which allows current flow through that resistor. So, all right, it's fully charged. So you can see it's 460 millivolts at 45 milliamps. So I thought my math was wrong there. It was. All right, I just released it, and there you go. I mean, hell, that's almost 19. That's about 19 volts right there. Well, not 19 volts, but 9 volts. So that's about 18 volts if it were fully oscillating. So again, it's a lot closer to FileStat. So, again, I'd imagine if this were a lower loss core, like if I'd use a common mode choke, because I had some various chokes in my junk box. I would have had to cross wired them, and this was just about the right value, right out of my junk box. So I thought I'd try it with this first. I didn't really expect it to work with this choke, but at any rate, but it does. So let's try turning the current up a little bit. Okay, 145 milliamps. Well, let me. I don't know if I feel comfortable with that. Turning it up to about. Let's turn it up to 70 milliamps to see what happens. All right, about 750 volts, 70 milliamps. Ah, nothing. Oh, there we go. I slipped. Okay. That's it's like what, 13 volts, so it'll be about 26 volts peak to peak there. Again, keep in mind I'm only doing with 2 volts here that I'm applying. It's all a matter of current. again, it's consistent. So yeah, it's like 12, 13 volts. I don't know what Falstat predicts because I haven't entered the information into it. But I'm still not in any danger of blowing my oscilloscope out. So let me go ahead and turn the current up to 100 milliamps, and let's see what happens. Alright, let me charge it up. Alright, there we go. Alright, so again, now we're getting a solid frequency reading. It says 5 kilohertz. And the voltage is, I can't read it. Okay, it's 31.64 volts peak to peak. Alright, and you can look, it's, you know, almost going off my scale there, and that's like 20 volts, so it should be about 40 volts peak to peak at least, if it wasn't such a lossy core. So this would seem to confirm my theory, you know, that it's a matter of how much energy we're storing in this choke and versus how much energy this small capacitor, you know, can absorb. So because the only thing the capacitor can do to store more energy is up its voltage, right? And that's what you're seeing here. And the inductor, you know, inductors are real funny in the sense that they will continue to apply whatever voltage they can to try to maintain that current. And as that capacitor charges up, well, that inductor has to work harder and harder and harder to get rid of all of its energy. But it will get rid of all of its energy before the capacitor can start throwing it back at the inductor. Because while that inductor still has energy in it, it is putting whatever voltage across it can in an attempt to try to maintain current flow. Even as that current flow continues to diminish, its voltage will still continue to increase until it's completely out of energy. And only then will it basically shut down like magic. You know, that's what's so freaky about inductors. That's why they always made me nervous, because they can do weird shit like this. And this shows that, because believe me, when I came into this, I was like, surely you can't generate high voltages with a tank circuit. But no, you can. You just got to go about it the right way. So, because if you think about it, my explanation that it's a matter of energy transfer between one and the other, and since this is an undersized capacitor, it's got to generate a much higher voltage to get rid of that. And because it's such an undersized capacitor, the inductor has to generate a high voltage, you know, to get rid of its energy. So if you think about it, it's perfectly logical why it works. I'm just gratified to see that it works in practice like Falstat predicted, because who knows? That's a free, cheap simulator on the internet, right? But no, I mean, we're getting up there in voltages right now. And again, I guess this thing can do 300 volts max. So let's try well, let me adjust the scale here. Well, yeah, 5 volts is as high as I can go on the scale. I guess I'm going to have to go to 10x. Okay, I'll have to go to 10x. So let's do it at 10x. Okay, 3.71 volts. Well, let me convert it to go ahead and convert it to 10x on the probe. Damn it. Still getting used to this scope. Okay. Anyway, rid of that. Let's see what it does. I got 50 volts per division. What do I have my trigger set down there? Well, it's probably not working right. Hold on. Okay, I messed up my settings on scope when I was changing that. But yeah, we can see, you know, we're getting you know, about 44 volts peak to peak. Now, I'm just having to translate for you. Charge it up again. Okay, about 37 volts peak to peak. So, alright, so let's go ahead and up the current to 150 milliamps. Okay, 44 volts, pretty solid. Now let me go ahead and up the current to, remember this capacitor that I got on here is only a 100 volt capacitor, so I can't go too high with it. We're already up to, things start exploding on me or whatever, because it's still storing a lot of energy. Okay, so it's 88 volts, or 68 volts peak to peak. So again, I think that even though I'm not using a good choke for it and everything, I would imagine if you used a higher, low loss choke, you'd get a lot more, oscillations, of course, before they dampen out. But you can see that, yeah, you can generate high voltages with a tank circuit. So, anyway, go figure.